So welcome back. And so we have a wonderful panel coming up, nuclear versus propulsion. This is a wonderful discussion because there's so many nuances to it. Not only just the technologies, whether we should, if we can speed up the trip to Mars, but they're also going to talk about things like orbital mechanics, how that should impact the decisions on how we should embrace nuclear propulsion and chemical propulsion, or the combination of both. And so moderating today will be Bhavya Lal, who's spoken many times to the Humans to Mars Summit. She's an associate administrator at NASA, which I can't remember the rest of the, but you can introduce yourself after. Since
I will.
But, thank you very much. I'm really looking forward to this panel. So, thank you.
Thank you, Chris. Can everyone hear me? I don't see anybody. There's just way too much light. But you're here. Awesome. Well, good morning. Welcome, everybody. My name is Bhavya Lal, as Chris said, and I'm the Associate Administrator for the newly created Office of Technology Policy and Strategy within the Office of the Administrator at NASA. Actually, just yesterday, or maybe it was the first day, our Deputy Administrator was here at Humans to Mars and announced that NASA has developed a set of framework objectives that will underpin the agency's plan to enable continuous human presence on the Moon, extended Mars analog missions in lunar orbit, and the initial human missions to Mars. She also noted that these specific objectives developed by our mission directorates will act as a guideposts over the next 2 decades as individual programs and technologies advance, and to help ensure that things we do are integrated and that we are staying focused on the goal. So one of the objectives that's in that document that is actually publicly available, so I hope you will all look at it, says develop a transportation system that crew can routinely operate from the Earth-Moon vicinity to Mars orbit and Martian surface. The objectives document does not say anything about what the transportation system will be, which perfectly sets up this morning's debate. What is the right way to get to Mars? Let's assume we are not looking too far into the future and antimatter drives are out. Let's also assume that we are not in the Star Trek universe, as much as I would like to be. And there's no dilithium crystals or a spore drive. Any Discovery fans here? Spore drive? So that leaves us primarily with nuclear fission and chemical propulsion options. Now we all know that nuclear propulsion has twice as specific impulse or propellant efficiency as chemical propulsion, which means we need to launch much less propellant, and less propellant means fewer launches, which means, among other things, lower cost. On the other hand, chemical propulsion is mature. We have it in hand, and the cost of launch is getting cheaper, so advantage chemical. But as you can imagine, it's much more complicated than that, which means we need a panel of experts to guide us. So let me introduce our panel. So we have with us today Hoppy Price, who is the Chief Engineer at NASA Jet Propulsion Lab and part of the NASA Robotic Mars Exploration Program. We have Tim Kokan. Is that how I say your last name, Tim?
Yeah, that's right.
Who is a Principal Engineer at Rocketdyne. And Tim is joining us virtually. And then we have Jonathan Cirtain, who is a Senior Vice President and the Chief Technology Officer at BWX Technologies.
Good morning.
Welcome to the panel, everyone. So I listened to a podcast called Intelligence Squared. I don't know if any of you do, and if not, you must download it this instant. So this organization hosts live debates to promote global conversations that enable people to make informed decisions about issues that matter. So we may try that style. Let's see how it goes. So with the caveat that these are not our experts' organizational or even their own personal positions, this is a friendly debate. Let me ask Hoppy Price to argue for chemical propulsion, Tim to argue for nuclear, and to make sure we are comparing apples with apples, Jonathan Cirtain will put on his scientist hat and articulate the metrics or the considerations that both sides will use as they argue for their positions. Are we ready?
Sure.
Awesome. So Jonathan, I will start with you. So the last official time NASA talked about about propulsion to Mars was over a decade ago. Hoppy told me that DRA-5 had talked about a conjunction class mission using nuclear thermal propulsion. And now if you read between the lines, this video that just came out this week, NASA is talking about an opposition class mission using a hybrid chemical and electric system. Note, we don't say nuclear, we just say electric. So how does one make this decision? What are the mission considerations? Jonathan, what factors should we be taking into account when making a decision between nuclear and chemical? What are the criteria? Tell us a little bit more, and then hopefully Hoppy and Tim are going to use those criteria as they argue for their positions.
Well, thank you, Bhavya. I think this is going to be a great opportunity for us to have this debate, and I look forward to being the scientist on the panel, as it were. So, chemical propulsion systems really are higher technical readiness, especially for cislunar missions. But a significant mission consideration for us for chemical is the needed in-space aggregation. So the mission system will have to be assembled on orbit, say, in a mid-Earth orbit, 10,000 kilometers or so out. And that might require up to 10 SLS-class mission launches, so 70 metric tons or so as currently configured for the Block 1 system for SLS. And that's necessary to get enough wet mass up, enough propellant in space. So while the technical readiness of chemical is high, the in-space aggregation and the number of launches is a pretty significant mission consideration. Second, for me at least, conjugation versus opposition class missions. That's a pretty important consideration that has to be made. It drives significant mission decisions, generally favors one propulsion system over the other, and then that goes to, once decided, mission, opposition versus conjunction, then you end up with mission duration being driven as a correlate or a related consideration. So for me then, having a mission duration consideration drives on-planet consideration. So then we're on Mars, we're there to stay for some period of time as a consequence of our orbital mechanics decisions, and that then is going to drive human habitation and fuels production. If it's a chemical launch, as an example, it's probable that we'll have to actually make the fuel for return when we're there at Mars, then requiring a pretty substantial amount of power to do that. Then my next consideration is mission abort scenarios. Even for the most exquisitely overfueled chemical mission, an abort is pretty limited. Most estimates I've seen are within days of mission takeoff that you would abort, so you're early into your cruise phase by the time you'd have to make that decision of whether to abort or stick with it for perhaps many, many months on your way to Mars, where a nuclear option might get you more abort scenarios. And then I think the final consideration that I would leave for Hoppy and Tim to consider is the diversity of mission concepts enabled by that decision we make. Things like nuclear electric propulsion, throwing the nuclear in where Bhavya left it out. While nuclear electric propulsion is the lowest technical readiness of the three in some respects, the enablement it has for some small science missions to explore deep into the solar system and for other options that suite of technologies would enable, I think that's a very interesting consideration that has to be factored in where we put our dollars. I think with that, I look forward to hearing what Hoppy and Tim have to say, and I'm gonna turn it over to Hoppy. What do you think, Hoppy? Or turn it back over to
So I
Bhavya.
actually was taking notes while Jonathan was speaking, and I heard 7 considerations: technical readiness, amount of aggregation needed in space, weather conjunction versus opposition, which has implications for mission duration, on-planet or on celestial body considerations, things like need for cargo and such, surface fuel production if there is that necessity, mission abort scenarios, and diversity of missions enabled for other things. So I think, did I miss anything, Jonathan?
That was it.
Okay, so those are the criteria. Before you even go into answering the questions, Hoppy, is there anything Jonathan missed?
No, I don't think so.
Okay.
Yeah.
Yeah, only a little few 7. Tim, anything Jonathan may have missed?
I guess, when I've done these kinds of mission-related trades in the past, we usually focus on things like performance, and that could be different depending on, if it's a launch vehicle or if it's a Mars mission. Cost, safety and reliability, development schedule, and then doing an uncertainty assessment of a particular solution. So I think Jonathan covered most of those with sort of an analog for performance and cost. Cost certainly on the number of launch vehicles. Reliability, Jonathan touched on it with the abort capabilities, but also just how difficult the CONOPS are for a particular mission. How many staging events do I have? How much propellant transfer do I have? Do I have to rendezvous with my return vehicle? Number of launches, obviously, number of main engine burns. All those things contribute to safety and reliability, right? And then development schedule, we've touched on that, the differences between chemical and nuclear. So in my mind, when we've done these studies, those are the kinds of metrics we try to assess and then compare. And then another key there I want to highlight is, how do you weight each of those factors? What's most important depends on the environment and the customer. Which of those is most important? Maybe for a human Mars mission, safety and reliability should be up there, right? At the expense of maybe some of the other metrics. So just some thoughts there.
Yeah, that is a pretty key set of criteria you added, Tim. One question that we often weigh is sort of, what are, risk of, humans in space versus risk of humans on the surface, and obviously how, that's a risk posture, which may be a political issue, right? Okay, so with that, and again, Hoppy, we don't have enough time to go through every one of those considerations. Whichever ones you think are the most important to discuss. So can you make the case for chemical to go to Mars?
Sure. So I'm not going to argue against nuclear propulsion. What I'm going to do is argue for chemical propulsion first, because I think it would do us well to start human missions to Mars sooner rather than later. And actually, my background is nuclear engineering. So I'm a nuclear engineer, and here I am arguing for chemical propulsion.
Me too.
But there was a National Academy study that was put out, written by Bobby Braun and others, about a year ago or so.
Jonathan and me.
Yeah, you were on there too. That's right. Yeah, and I was thinking of Bobby because he was at JPL at the time. But anyway, I think that's a really outstanding report, and it really lays out, the advantages and also the challenges of nuclear propulsion. And, my takeaway from that report is that, it's going to be a while before that's ready to have systems that are human-rated and ready to actually transport crews that have, the reliability and the radiation protection and, everything you need to do a crewed mission to Mars using nuclear propulsion. And I think it's possible for us to do chemical missions to Mars in a more minimal architecture, within the next 15 years. And so in order to do a chemical propulsion mission, you need to launch about 750 tons worth of chemical stages into Earth orbit to aggregate, a system together to do a completely self-contained mission to Mars. So you don't need to do ISRU on Mars. You have all the propellant you need. And so there's an architecture that I've studied over the past year or so that requires about a dozen or so launches of chemical stages by commercial launch vehicles, and then 4 SLS launches in order to conduct a human mission to Mars. And I was particularly focused on the 2033 opportunity, because that opportunity, you can do a 570-day mission, 1.6 years total duration, but that happens in 2033 and doesn't reoccur again for another 15 years. So that's really a great opposition class mission opportunity. And Boeing has studied a flyby mission for 2033. I've studied an orbital mission in 2033, and I believe those are feasible and could be considered. And when we look to the long term, when nuclear propulsion is available, I think there are a lot of advantages to using that. But when you look at the opposition class missions versus the conjunction class missions, for these sweet spot years like 2033, They are a lot shorter, but there are a number of years where the opposition class missions require so much delta V that even with nuclear propulsion, you probably can't do the missions in those years. So the conjunction class missions offer you a similar opportunity with the same kind of system year after year. Every 2 years you can continue doing that. With the nuclear systems and doing opposition class missions, every opportunity is different. Some of them have twice the delta V as other opportunities, and they have different lengths of mission time. But I think for the nuclear propulsion doing opposition class missions, what ultimately may be feasible are total mission durations of about 800 days. And I think that's compared to conjunction class missions, whether they're chemical or nuclear, of 950 to 1,000 days. So you are saving some time in the total mission duration, but is it really that much? Is it a big difference to have an 800-day mission versus a 950-day mission? And the other consideration is transit time. So for the conjunction class missions, it's 7 months each way, and then you have about 550 days on the surface of Mars, and you need to have a habitat and all the consumables to have people live on Mars for a year and a half. But there's a lot of great science you can do in a year and a half on Mars, a lot more than in 30 days for the opposition class missions. But for the opposition class missions, typically the return leg is much longer than 7 months. So when you look at the total transit time, the total amount of time you're spending at 0G and being exposed to galactic cosmic radiation, it may actually be a little bit less advantageous for the opposition class missions because the times in transit are longer. And I think it's better to spend more time on the surface of Mars where you have 1/3 gravity and you do have some considerable shielding from galactic cosmic radiation. There is still radiation on Mars, but not as much as in transit. So, it's a very complicated picture. And for me, when nuclear propulsion becomes available, I think it could really have a great utility in doing conjunction class missions, the long stay missions, but using that extra delta V just to shorten the transit time. So instead of a 7-month transit time, maybe you have a 5 or a 5.5 month transit time, and that could be very beneficial.
Thank you, Hoppy. Tim, do you have any questions or pushbacks for Hoppy? This is a debate.
It is, but I agree with most everything Hoppy said. One question I'd have for Hoppy is, so you talked about starting with chemical because you can start there early, but you still like nuclear. Mm-hmm. What are your thoughts on starting with chemical and how you'd smartly transition down the road in future missions over to nuclear? What can you leverage from a chemical system?
So if the mission architecture that I've been looking at has a transit habitat and also a capsule type lander, and I think those things would stay the same. So if you did the chemical mission, you're proving out the transit habitat. I think each mission you're probably going to tweak the design of the transit habitat and improve it and solve the problems you have in the previous mission. So that system will evolve over time. So I think it's just a matter of replacing those chemical stages with a nuclear stage. So the architecture that I've looked at has about a dozen commercial launches of identical chemical propulsion stages. So you got a dozen launches, but each one is identical. It has the same around 50-ton chemical stage and the same launch vehicle, so you can kind of mass produce those and even have a couple of spares. And so when nuclear is ready and it's ready for crew, I think you just replace those stages with the chemical stages. But the transit habitat, the lander system, could be the same. So, you've just proven those things out in the earlier missions and gotten some missions under your belt, which I think is useful.
I guess another comment I might make is, with either chemical or nuclear in-space propulsion, you're going to need power on the surface of Mars, and it could be solar, could be nuclear for either case, for either chemical or nuclear in-space propulsion. Hoppy, just wondering your thoughts on the options there for surface power on Mars.
Yeah, so if you did a sort of a stepwise progression of missions like Apollo did, where you have the Apollo 8 mission, you do an orbital mission at Mars, you could have Apollo 11 mission where you do the first landing mission on Mars, could be a 30-day sortie mission on Mars. For that, solar power is fine. It's probably the cheapest and easiest. But when you start to do the long stay missions, which I think is where we need to go for human exploration of Mars, especially when you have these opportunities that don't have 570-day total mission duration, you have to be able to survive dust storms on Mars, and they are not real predictable as to when they happen. And the Opportunity rover lasted for 13 years, solar powered. It had some cleaning events, but the InSight lander didn't have such good luck, and so it's probably going to shut down in a few months just because everything is just caked with dust and you can't get solar power. Now with crewed missions, I think you do have opportunities to clean off the solar arrays, but when you look at what finally killed Opportunity, it was not dust on the arrays, but it was the dust storm blocking the sun in the upper atmosphere, and there's nothing really you can do about that. So if you have a crewed mission to Mars, it's a 550-day mission, you have a global dust storm, you have to have nuclear power in order to survive that. Even if your solar panels are clean, the sunlight's still not coming down because the dust is blocking it. So either you'd have to abort to orbit and get back to your transit habitat, or the best option is to have nuclear power on the surface of Mars so you can have assured power and also provide thermal energy during the night, because for 13 hours every night on Mars, you have to heat your system, and it gets really cold at night on Mars. So having nuclear power, whether it's a fission system or advanced radioisotope systems, with dynamic power generators, I think you need nuclear power on the surface of Mars for crewed missions.
Jonathan, do you have any questions or clarifications? Did he address the most important of your considerations?
So, ironically, I'm going to be the one that was with the considerations, but I'm going to poke at Hoppy where Tim missed the opportunity, in my opinion. I do think that mission duration is something that strongly should be considered when either going commercial or going chemical or nuclear. And because of the variability in conjunction versus opposition class opportunities, the variability in solar output, the 11-year solar cycle, drives those decisions to some degree. The amount of radiation, the solar wind output during those events, the number of flares and coronal mass ejections during that cycle does pose different risks in a conjunction versus opposition class mission timeline, depending on when those are going to occur. So in 2033, you're kind of in a period of time when the sun is more active. Consequently, your duration in space should be limited so that the probability of occurrence of a coronal mass ejection going through that part of space has to be considered. As a consequence, I would say that chemical, in some instances, may make sense, and certainly the technical readiness drives it forward as opportunity now.
Right.
But I would say, Hoppy, really, can you always depend upon chemical as that solution, given all of the exigent circumstances that have to be addressed in those different mission archetypes that you would employ that propulsion
Right,
system?
yeah. So when you talk about solar flares, I actually think the conjunction class missions are better because you stay outside 1 AU. For the opposition class missions, even with the nuclear propulsion, you need to go in about the orbit of Venus. And so if you have a solar flare during that time, it's much more severe. Although I think they're survivable. If you have a shelter where the crew can huddle down for 2 or 3 days during a coronal mass ejection, I think that you can safely provide that for the crew, where they can kind of hunker down for a few days when you have a solar flare. It makes it more difficult if you're going into Venus than if you're staying outside 1 AU. The galactic cosmic radiation, there's not much you can do about, and that is more severe in transit than it is on the surface of Mars. So I think just reducing your time in transit is what you want to do for the GCR, the galactic cosmic radiation. And again, I think the conjunction class missions have an advantage for that.
So GCRs actually are modulated when when the sun is actually more active, because the heliosphere is larger.
That's why we got a scientist on the panel.
that plays an engineer
Yeah.
at work. Yeah,
Right,
so,
right.
where 2 engineers are playing. So
Yes.
anyway,
Yeah.
Cool. Okay, so I think we heard an argument for chemical, although I understand the argument was much more for a conjunction class mission
Yes.
than necessarily for chemical. Fair point. Tim, over to you. You know, given again the considerations that Jonathan mentioned, the ones that you added to, you know, how do you propose, you know, what is your argument for nuclear propulsion? And again, we can get into the NEP, NTP issue, but maybe start with just nuclear first, and then if we need to, we can talk about the NEP, NTP schism as well.
Sure, sure. So, you know, as we've said, nuclear propulsion, its higher performance in comparison to chemical results in several clear advantages. One, a smaller in-space vehicle to do the same mission, right? Which means fewer launches, which means lower launch costs, which means increased mission reliability. Alternatively, you could carry more payload. You could have a bigger habitat. You could have larger, you know, surface elements if you're using nuclear for the cargo delivery as well. Increased performance, right? In that case, wider launch windows. If you've got the higher in-space propulsion capability, you can afford higher launch windows. It's not as painful, right, as compared to chemical. We mentioned faster transfers, and that's obviously a safety and reliability benefit there. Certainly safety for the crew in terms of limiting GCR. Another benefit of high performance propulsion is that you can carry all your propellant with you to Mars. You can carry your return propellant with you rather than most chemical solutions will pre-position the return vehicle or return propellant at Mars. So you have to rendezvous with it in Mars orbit to come back home. If you have higher performance in space propulsion like nuclear thermal or nuclear electric, you can typically, it's not as painful to bring the return propellant with you. And that buys you a few things. One, it's easier ConOps because you don't have to rendezvous with your return vehicle at Mars. And two, it significantly increases your abort capability. We did a study a couple years ago looking at a typical chemical and a typical nuclear thermal type mission. And chemical where you pre-position your return propellant, and nuclear you bring it all with you. And the impact on how far after your Earth departure burn can you come back home? It was like 5 days for chemical and 3 months for nuclear thermal. So a big difference in abort capability that's enabled by that higher performance in space propulsion. Let's see, what else? So the other thing, we mentioned this, the kind of the variety of missions you can do. So those missions, all the conjunction missions, and then, if you choose smartly with the opposition class missions, nuclear solutions can support all of those, right? And you can come up with vehicle designs that are sort of modular, that you're able to, with drop tanks, number of drop tanks, for instance, you can do a conjunction mission or an opposition mission with kind of the same core vehicle. So, what architecture makes sense? We've talked about conjunction and opposition. I sort of, kind of the work we've been doing, we've been looking at a campaign, a series of missions where you have a vehicle that maybe it starts with opposition because you want to have a shorter surface day or a shorter overall mission for reliability reasons or surface infrastructure development reasons. And then you use that same vehicle, you take it to Mars, do an opposition class mission, come back home, refuel and refurbish it, and use it for a conjunction class mission or a series of conjunction class missions. So this ability to bring all your propellant with you allows for makes reusability easier because you don't have to stage stuff off on the way to Mars and back. You're not doing a direct entry into the Earth's atmosphere that some configurations have. So really, there are a lot of benefits with high performance in-space propulsion that you can leverage kind of across the board.
Hoppy and Jonathan, feel free to push back. But one question I have, Tim, and it relates to what Hoppy had said. Chemical systems are relatively mature, even with the point that Jonathan made about a lot of, coordination needs to happen in space to get all of those tanks hooked up, et cetera. And nuclear, as we know, is early TRL. How do you kind of make that trade-off? Something that's ready, it's a devil we know, right? Versus something that needs to be developed, which in my mind is, in principle, we could go sooner with chemical. And again, I have no views here. I am playing devil's advocate, intelligence squared. So sooner versus better, I guess, would be the trade-off, right? How do you?
Yeah, I think that's kind of one of the main selling points of chemical is that you can go sooner. In terms of a lot of the other metrics, nuclear looks better, but that development time is a significant advantage. I guess I would say that there's actually a lot of technology development work going on right now within NASA and with DoD and within DoD on nuclear, both thermal and electric. And while there is a gap, as we invest in nuclear, that gap is shrinking. That development gap is shrinking because the TRL is increasing both on the nuclear thermal and nuclear electric side. So yeah, absolutely. Right now, chemical is higher TRL, but we're slowly advancing the nuclear technology, both power and propulsion, so that gap is shrinking.
Thanks, Tim. Questions from Jonathan and
I guess I would ask both Hoppy and Tim, the in-space aggregation requirement for either kind of is outside which choice of propulsion system you make. So how long is it to develop the in-space aggregation capability? The management of that fuel that you would take with you, either propulsion use case, is something that is TRL that we don't have, or is technology that we don't have right now. So what would it take for us to get to a place where we have in-space aggregation capacity in 10,000 kilometers or so, where we could put either system up, do that in-space aggregation and assembly, and be ready to go with either? Because if that's 10 years away, then nuclear may be able to catch up with chemical. If that's 2 years away, then maybe nuclear could not catch up with chemical. So Hoppy, where are we with that?
Yeah, I don't think that the aggregation problem is that difficult. Certainly, that's going to be demonstrated away from Earth at Gateway. There will be things that are aggregated there. And so, again, I think that's another reason why Artemis is an important program and Moon to Mars is to go ahead and prove that capability. But, given where we are now at rendezvous and docking, and, we've assembled a space station, SpaceX is planning on using tankers to refuel their starships in Earth orbit. So I don't think the aggregation is such a problem. And for any system that goes to Mars, whether it's the SpaceX Starship, whether it's nuclear propulsion, whether it's chemical propulsion, you're just going to have this aggregation problem. So, the architecture that I had proposed for a 2033 mission did have a lot of boost stages. They were identical chemical boost stages to try to get everything up to high Earth orbit and aggregated there and off to Mars. But once that's all set and you're done using all those boost stages, which can have backups, and redundancy, when you're ready to send the crew up, there really is no more aggregation for a conjunction class mission. Once the crew gets to high Earth orbit and you have your system there, you're off to Mars, you can do your whole mission, you can come back, you don't need to get propellant at Mars, you don't need to rendezvous with any stages at Mars. For the opposition class mission though, it is different. So for a chemical propulsion system to do an opposition class mission, you have to pre-position chemical stages in Mars orbit that you must rendezvous with in order to get back home. Yeah. But so it's just a matter of how much propellant you need to launch and how much aggregation you have to do in Earth orbit. And so, Bhavya, one of the questions that you asked, that you haven't asked today, but in our emails, you said, well, if you can do this mission with chemical propulsion, why haven't we done it yet? And I think that's because in the past, we were looking at Saturn V's or Ares 5s or SLSs to launch 750 tons of propellant to Earth orbit, and that's expensive, because those vehicles are not cheap. But what's changed in the last 10 years are these commercial reusable launch vehicles that have dramatically cut the cost of launching propellant into space. So in the architecture that I was looking at, we had about a dozen identical launches of commercial chemical stages, but those are a lot cheaper than launching on an SLS.
Right, and if you believe the hype, the launch costs will get a lot cheaper going forward. So.
Yeah, but the thing is, right now with the Falcon Heavy, the launch costs, I think, have already come down a lot, enough to enable a chemical mission to Mars. And then, if we have the Blue Origin New Glenn and the Vulcan vehicles, there may be that competition in commercial vehicles, and as you said, prices could even come down more. So now you're weighing the cost of launching propellant, which is getting cheaper, versus the cost of the nuclear engine, the system, which is more expensive than a chemical system. So it's a pretty complex cost proposition to figure out what is the best business case.
Yeah, that's actually a really good point, and one I wanted to discuss a bit. We may be having what is called breaking the premise, right? Everything in the space sector is driven by sort of lowering launch costs. Mm-hmm. So space systems have to be so light because it's so expensive. And it seems that we are starting to break the premise.
Yeah.
The other thing that's happening, which again is sort of a breaking the premise, we wanted always these monolithic architectures because they were low risk, but now as AI, ML, robotic, and automation tools get better, maybe we can do more in space. Maybe in-space assembly would be lower risk than we have estimated in the past. Mm-hmm. Any thoughts on these sort of changes that are coming down the pike? And again, we can just go down, Jonathan, Hoppy, and then Tim.
Well, I do think that new technology in design space, in engineering test space, is decreasing the time to deploy a new technology. I think we're seeing that in nuclear. The number of new companies that are looking at advanced nuclear systems and actually getting to the place where they're testing real content is dramatically increasing. So those cycle times to get new nuclear out there, I think, is coming down. You're seeing the same thing happen in chemical motors. So I think a lot of the new technology enablement that's coming with the capacities provided through machine learning and artificial intelligence are really striking. The other thing that I think is driving that is materials. There's a lot of capacity to use advanced materials for space manufacturing, for manufacturing systems for space that are really allowing us to do new and novel things. I think Lockheed Martin just demonstrated a hypersonic vehicle that really does test the bounds of material science and has done so successfully. So I think there's a lot of new capability out there that's driving down the timeline to deploy new content and also making for more advanced vehicles. One thing that we've not mentioned yet is as the efficiency of nuclear systems improves, that's being driven by the operating temperature of the reactor. So we're getting to where we have materials and designs for nuclear systems that really drive that fuel efficiency into really high numbers. Also getting us improvements in the change in velocity, the delta V. So delta V's of order 1,000 meters per second are now possible. Fuel efficiencies like Tim mission ISP that are quite high for NTP and extraordinary for NEP are really less than a decade away with significant investment. So I think there's lots of opportunity there. I think Hoppy's right about the in-space aggregation thing. It's really name the time and we can go do it. So that's kind of the way I'm thinking about it, Bhavya.
Thanks, Jonathan. Let me switch to Tim so I can uncrick my neck, and then back to Hoppy. Tim, what are your thoughts on that sort of the whole breaking the premise concept that all these things we were basing our assumptions on may not be valid?
Yeah, that's a great point, and you know the point Hoppy made about launch costs decreasing and that impacting you know the relative benefit of a lighter vehicle. If you were you know really driving, you don't maybe necessarily have to have you know try to minimize the number of launches in order to minimize costs. The other part of that though that I brought up earlier was reliability of the system and just number of launches, rendezvous and docking maneuvers, hooking up, you know, propellant transfer, whatever it is. That impact, in addition to cost, probably more so than cost, is where you'd like to try to make your aggregation as simple as you can. Obviously, you know, both nuclear, thermal, nuclear, electric, and chemical are all going to have aggregation because we don't have a 700 or 1 million pound, you know, 1,000 metric ton launch vehicle that's going to deliver that in one shot. But I think it's important to keep that safety and reliability metric at the forefront when we're talking about, especially human missions to Mars. And there are advantages and disadvantages of both, but I think that's key to keep in mind.
Thanks. Hoppy, any other words on?
Yeah. So I think what Tim just brought up about reliability and crew safety is very, very important. And so, and it's important to distinguish between critical docking maneuvers and critical aggregation versus non-critical operations. So when you look at SpaceX's architecture, where they have to have many, many launches of a tanker to refuel it, those aren't mission critical operations because you can launch another tanker if one of them doesn't succeed. But what's important is after you get the crew there, then you want to maximize the reliability and minimize the number of critical operations that have to take place. And so that's the reason why in the architecture that I was looking at for a chemical mission, there are all of these commercial launches of boost stages, but none of them were mission critical. But once you finally got everything up into high Earth orbit, that's when really operations become mission critical for the crew. And so you want to minimize the number of aggregations that have to take place after that point. And so I think you can optimize a mission for safety that way. And also looking at safety and reliability, that's important for nuclear versus chemical. So if you have a nuclear system, what is the reliability of that over the length of the mission versus a chemical system? And I think we have to consider what is the safety and reliability of those in flight. What is the possibility? What are the probabilities of loss of mission, loss of crew, the LOC-LOM metrics that we use, and those are an important consideration in the whole mission architecture.
Completely agree. So before I ask my next round of questions, we have an audience here. You all heard about criteria and metrics that Jonathan talked about. You heard about the case for chemical that Hoppy touched on, and you heard about the case for nuclear. Did our experts miss any criteria or any arguments? And again, I can't see hands very well, but if anybody wanted to come to the microphone and say something. Because I think one of the things we don't do as well in the space community is get, the public telling us what we should be doing.
Hi, Jerry Sanders, NASA. One for each side. So Hoppy's chemical now, nuclear future, missed the life cycle cost aspect of having to recertify human systems for another generation. The nuclear discussion completely missed the volumetric and hydrogen storage aspects in space versus a softer cryogen with, say, oxygen and methane. So I would throw those 2 points out to each of those.
Thank you. AJ, did you have any things we missed?
Yeah, hi. My name is AJ Kothari. One possible aspect is that probably is not mentioned is sort of a repurposing of a nuclear propulsion reactor, etc., into an energy producing situation where wherever it lands, and at least the reactor part is common. And if you want to create just simply nuclear thermal energy, that can be done. And if you want to create, obviously, electricity, you have to take turbines with you. But at least the first two things can be done with nuclear. That would not be possible to do with chemical, unless you take a lot of oxidizer with you, which is more expensive. So that's an advantage of nuclear, as I would see it. And thorium, molten salt reactor, for example, that exists, thorium exists on the moon a lot. So all of that can be combined together to be able to produce energy at the same time using the propulsion methods. Thank you.
Thanks, AJ. Any other comments? You go ahead. Oh, sorry, were you there first? Go ahead.
Morning, Robert Howard, also NASA. Sort of a follow-on to Jerry's point. In addition to cryo storage, I'd also be curious about the implications of storage of hydrogen versus methane. And you referenced electric thrust a couple of times. I'd also want to hear about the availability of xenon versus argon and the efficiency of the two relative to each other.
That's actually a question there as well. Does anybody want to take that on, those two questions?
So I'll go to Robert's question about the xenon propellant. You know, getting the xenon really isn't that difficult. It's just a matter of putting out an RFP for people to deliver xenon, and it's really a byproduct of the liquid air industry, which is worldwide. And so, you know, it's just a matter of one of these liquid air factories, you know, providing a tank to collect the xenon, because it's a waste product of making liquid oxygen, liquid hydrogen, dry ice, all of these things. So, you know, we found that if you put out a contract years in advance, you'll have plenty of people that want to bid on that competitively to deliver the xenon. So getting, you know, many tons of xenon, I don't think that that's really a problem. Let's see, I'll go to Jerry's question about technology, you know, and so he was saying that, you know, once we get one system like a chemical system, that NASA or space agencies will never change. They'll always use that system. They'll never on-ramp another system and human rate it. And you know, I would hate to think that, you know, as a space society, we're stuck in that kind of a situation where we'll never bring on new technologies. I think we need to be able to go and do missions with what we have now, and be able to take advantage of new technologies like nuclear when they become available. I don't see any reason why we can't do that. You know, going to Mars has always been 20 years in the future. In 1970, it was 20 years in the future. In 1980, it's 20 years in the future. And now it's 20 years in the future. So I think, you know, we have the technology now to go do missions to Mars, and, you know, let's do a mission, you know, and then when other better technologies become available, let's bring them on and do better missions.
Hey, I feel for you, Hoppy. I was studying nuclear engineering in the mid-1980s, and fusion power was 50 years out, and I understand it's still 50 years out. So.
You know, maybe now it's only 40 years out.
I think it's important for the broader audience to explain some of the details behind the questions, because those are they were a bit specific. A nuclear thermal propulsion system's propellant, if you will, is hydrogen, cryogenic hydrogen. The way that the system is meant to work is you store a cryogenic hydrogen at roughly 19 degrees above absolute zero, and then the higher that you can heat it, that change in temperature is directly proportional to your fuel efficiency. So, you know, operating reactor systems intended for NTP, nuclear thermal propulsion, are meant to get to close to 3,000 Kelvin. So large change in temperature, highly fuel efficient. So you need cryogenic hydrogen for those reasons. Argon, xenon, those are the propellants for a nuclear electric propulsion system. So the higher noble gas weight of xenon gets you more bang for your buck when you accelerate it out the thrust nozzle. So those are where those questions are coming from. I think the consequence of AJ's question is the decision that you have between nuclear thermal and nuclear electric. If you wanted to use the reactor system for power production, for electricity production, you would really need, that would not be an NTP system easily, simply in the way that high temperature gas reactors notionally work. The system that you'd have to carry with you to convert that thermal energy to, or its working fluid to something electric would be very different than what you would do if it were a nuclear electric propulsion system, which is already creating electrical power to accelerate the xenon through that type of system. So several different considerations baked into those technical questions.
Yeah, no. So thank you for clarifying. I think it's important to understand those distinctions. So thanks for clarifying. Actually, let me just go to Tim and see if he has any comments to add, and then we will go back to a round of questions.
Yeah, one comment about the electric propulsion and the propellant choice, xenon versus argon or krypton. Certainly, xenon's going to be higher efficiency than the other two, but you do take an efficiency hit. Now, if there's you come into a situation where, for whatever reason, you can't produce the amount of xenon you need for a mission, you could go with an argon-based solution, and it would have, a few percent lower efficiency, but you can typically, when you're doing a mission design, you can deal with that.
Agreed. Okay, there was one more question.
I just wanted to point out one thing about the chemical systems that I think can be a little bit of a fallacy. Accepting Hoppy's purely storable architecture, any architecture of a chemical system that relies on ISRU for producing propellant to come back, namely the cryogenic ones, or for storing cryogens in long-term use out at Mars and then for return, is going to require a lot of power. And those systems are likely, especially the surface systems that need to produce propellant at Mars, are going to require nuclear power.
Yeah.
So that comes back to the whole point of we do need those nuclear surface power systems.
Absolutely, yeah.
So just
I think
wanted to put that.
Yeah.
Another question?
First of all, thank you all very much for hosting me. I'm in a related industry, not this industry, and it's a fascinating conversation, especially if you're not an engineer and you spend a lot of time researching what all the nons are that we're talking about today, the argons, the non-nons. I'm really curious. One of the things that I've heard throughout the conference is raising awareness, raising money. These things are complicated. We've got the engineering staff, and I'm reminded of the early days. My dad worked on shuttle for 25 years, on station for 15 years. I know that in a lot of those systems, those are 20, 30-year-old systems, and one of the reasons why he was able to work to his 80s is because they didn't want to replace the systems. There wasn't a lot of appetite for risk changing something. And where we grew up, we knew Joe Walker, Don Malik, Chuck Yeager, all these experimental fighter pilots. And I'm wondering, as you talk about propulsion systems, if you want to capture the imagination, so that's my comment. My question is, when you want to capture the imagination, people like me who are really interested in where are we exploring and how are we going to do the next thing, and maybe in 20 years we can get to Mars or whatever's next. In this conversation about nuclear or chemical, how do you present the conversation where it's not just about the engineering, but it's about human beings are people who explore and challenge and do new things. And by that I mean, it may be obvious to engineers or those close to the community, but that spirit of taking ships built for the Mediterranean and selling them out into the open sea or challenge, right? When we build and iterated on these explorations, the final craft had a perfect system to take large crews, but the initial craft were dangerous and small, just like we did in our space program. So as you think about presenting, whether it's chemical or nuclear, to the public, how is it that we capture their imagination to where they want to get on board with either system, either the tried and true, the existing, or the emerging and new, so their imagination is piqued and sparked, and how we can show a benefit, whether it's to a nuclear program or a chemical program to us on Earth. And by the way, it seems to me we've been doing nuclear in the Navy for 40 years, for months at a time in closed, sealed, dangerous environments. So anyway, thank you very much for letting me attend. I'd love to hear your responses to those.
Thank you. You made a bunch of really, really good and important points. As I mean, I think all of us here are engineers. Probably a lot of you all are engineers as well, or scientists. And we just love to get in the details right away. But we really do need to start with, why are we going to Mars? It needs to be a public conversation, and we need to do better. At least that's my view. I don't know if the panelists have any thoughts on that. And the other point I also wanted to make was your point at the end about, we always want to go straight to the Ferrari without going through the Model T stage, right? And that's why we have all these really incredible constraints, 3,000 degrees exit temperature of the nozzle. I mean, we are pushing the limits of our knowledge. Would it be better to start with a smaller system? Maybe start with power, and test it. And again, it's not just the engineering, but there's also a policy and regulatory framework, right? We have never actually launched, at least in the last, since 1965 when we launched the SNAP-10A reactor, and which at the time we didn't have the regulatory framework. We don't know how to really do it. So we need to test. So I would agree we should start small, do something sooner, which I think was Hoppy's point, and move forward. But I would love the panelists' thoughts on feedback or comments on our latest question, which is a really good question.
Yeah, I think it's very important to address our risk posture. So when you look at the Apollo days, I mean, we did Mercury, Gemini, Apollo, all in less than 10 years, these different vehicles. So, we shouldn't lock into this concept that we're going to design this one vehicle to go to Mars, and that's all we're going to ever have and use that forever. If you look at SpaceX, they started with Falcon 1, Falcon 9, Falcon Heavy. Now they're moving on to Starship, and they do things very quickly, and they are not risk averse, and so they're not afraid to blow something up to do the test. To me, another shining example is the Krusty reactor experiment, where a small group of people did a prototype of a surface power generating system for the Moon or Mars, and they did it for tens of millions of dollars in a very short time, and had a very successful test. And that was, they raised the TRL level of surface nuclear power by a lot in one cheap, fast experiment. So, I think we need to be a little bit more of a risk takers in a way that's still safe for people, but not be afraid to rapidly advance our technologies and take a few risks, and not be afraid of having a few failures along the way, and learning from our failures, which is exactly what SpaceX does.
I'm going to take my scientist hat off for a minute and be a capitalist. I believe one of the answers to your question is commerce. We're seeing the in-space and space-to-ground commerce boom occur right in front of us. The number of venture capitalists willing to put cash into deploying things in space is outside just a few billionaires now. So there are a lot of folks making those investments. And as we make those investments, it's inherent in the DNA of the United States to protect our interests. So the reasons why we would want to put more content in space is one of the fundamental aspects of the U.S. federal government to protect commerce. So in cislunar space, there's one reason why we should be developing new and advanced capabilities. That same thing goes for Mars. If we want to see commerce extend outside of near-Earth orbit out to the Moon and then on to Mars, the development of these technologies by the U.S. government and by other governments to support that commercial growth is a requirement, I feel. The same thing happened when we first voyaged from wherever we came from to North America and then across North America. First we put a fort in place, then commerce grew up around it. The United States should put forts in place in space, make sure it's safe to do commerce. The requirements of those are outside chemical. You need nuclear, you need other things as well to make sure that it's safe for people to put their cash in space, for people to go out there, make money, and bring that back to the U.S. So I think as a nation, we have to come to terms with the fact that the population of the planet is expanding into space, and as a consequence, we need to make sure that our interests are protected.
And I would just comment that that's the history of the world. Whether you go, whatever empire you go back to, how can I invest my money in the caravan that's going out there? There's an opportunity for me to change my personal income status. It's an opportunity to be part of something new. There are always people to do that. I just feel like there could be a better opportunity. Maybe I've just been living in the wrong place, listening to the wrong things, about how do I, to your point, how do I participate as a citizen in this fantastic endeavor for all of the reasons that you just laid out. I think there's a compelling story there that's not an engineering story. It's a human exploration story that people love to get behind. And we've got at least 10,000 years of written history that show this is how we change the world for the better. So thank you very much for your comments. I appreciate it.
Well, I don't think we can top that. So I would like to, and unless, Tim, you have anything compelling to end, I just think that's a really good place for us to have, to pause this discussion. Obviously, it's a to be continued. Tim, any final points you want to make?
No, I think we hit on a wide variety of topics. I thought this was a great conversation.
Well, please join me in thanking our panelists.